Hi guys, I am Yashodhan Agnihotri, a final year student at IIIT Pune, and I will be your host for today. Welcome to our channel, Learn Competitive Programming with CodeChef. On this channel, we post weekly problem explanations and concept videos. Also, if you are interested in competitive programming and want to master data structures and algorithms, this is the place for you. So, what are you waiting for? Click on that subscribe button and kickstart your journey towards competitive programming today.
So the problem in discussion today is from the recent February Long challenge, and the problem name is another tree with number theory. The difficulty level of the problem is medium and the prerequisites are number theory and pre-computation. So let us see the agenda for today. First, we will try to understand the problem statement. Next, we will see the detailed solution approach. Lastly, we will be seeing the C++ implementation. Now, let us try to understand the problem statement. You are given a rooted tree with n nodes numbered 1 to n. Okay, so node 1 is the root. So let us call the root node 1. For each I from 1 to n minus 1, the parent of the node I plus 1 is given as pi. So this is our input. Now we need to answer q queries. So let us see what each query is. For each query, first W tasks are given to node V. Now let's see what exactly, how can we process these tasks. So when a node receives A tasks and it has no children, then all A tasks are executed by this node. So say suppose, so node 2 receives 10 tasks, then node 2 has to execute all of them. Now, if the node has k greater than 0 children, so he has like a positive number of children, and k is a divisor of a, so a percent k is equal to 0. This condition holds. Then this node gives a by k of these tasks to each of its children. So let us consider something like this. Okay, and let us see that 2 gets 10 tasks. Now it distributes 5 tasks to node 3 and 5 tasks to node 4. So let us move on to the next condition. Otherwise, if the node has k greater than 0 children but k is not a divisor of a, so now the condition is a percent k not equal to 0. So let us see, sorry, not 3, 5, and 1, 2, 3. So now let us consider that node 5 gets 10 tasks, and as it has 3 children and 10 is not divisible by 3, then all the A tasks are ignored and none of these node children receive any tasks. So all 10 tasks are ignored. Okay. Now, for each query, we should find the number of tasks that are not executed, that is, which end up ignored, possibly after passing down the tree. Now, I've explained you the problem statement, but to understand it more clearly, let us look at a proper example. Now, let us try to understand the problem better with the help of a sample case. So here I have a tree which looks something like this, and I've been given a query on the first node where the number of tasks to be executed are 36. So we start with 36 tasks. Now it has 3 children. Cool. So all the tasks will be divided equally. And as 3 is a divisor of 36, it gets 12, 12, 12. Now let us start with this node. So 2 again has 2 children. Node 2 has 2 children, 5 and 6. And is the number of children a divisor of the number of tasks? Yes. So 6 tasks and 6 tasks. Now again node 3 has 2 children and the number of tasks is again divisible by the number of children. So 6 and 6 over here. Again now 5 has 2 children, so it is again divisible, and 3 and 3. So if you see, all the tasks are completed by the leaf nodes. Hence, no tasks ends up being ignored, right? Because even node 4 executes its task itself because it has no children. So the first condition. Now say over here we had a case that node 4 had 1, 2, 3, 4 and say 5 children. So 12 is not divisible by 5. Therefore, all these tasks will be ignored, right? So for our original tree, the answer for this query would be 0. But for this tree, the answer would be 12. So I hope the sample case and the problem statement are clear. And with this, now we will move on to the solution approach.
Also, did you know that CodeChef conducts free live classes on Unacademy where we teach every possible topic related to competitive programming? We have basic level courses like Introduction to C++ or Java, Recursion, Basic Data Structures, as well as advanced level courses like Dynamic Programming, Segment Trees, and Graph Theory. These courses are conducted by top coders who have been ICPC finalists, IOI medalists, or work in top product based companies like Google, Facebook, and LinkedIn. All you need to do is download the Unacademy app or register yourself at unacademy.com and choose your goal as competitive programming. You can also take the paid Plus subscription to get additional features and individual level support. In Plus, we have a large set of practice problems associated with every topic covered. Also, we have 6-star and 7-star rated teaching assistants to help clear all your doubts before, after, and during the live session. You can use my referral code, which is ZAP10, and get an instant 10% off on Plus subscription. So hurry up, guys. Don't miss out on this amazing opportunity and kickstart your journey towards competitive programming today.
So to begin with the solution approach, first let us fix this that all the tasks that will be executed, they will be executed at the leaf nodes, right? Because each node, if it has a child, it passes on the tasks to its child or children, whatever. So if a task gets executed, it gets executed at the leaf node or else it is ignored. Now, in this tree, so in this particular, not particular, I've taken it as an example. So in this tree, uh, you can see that node 4 has just one child, that is node 5. So now what is exactly, what I'm trying to say over here is 2 has two children, 3 and 4 has just one child, that is 5. So whatever task 2 gets, say W, it will pass on to 4, that is W by 2, uh, if W is divisible by 2, and 4 will pass on the same number of tasks, that is W by 2 to 5. So what we can do is, all the nodes which have just one child, we can just merge those child into the node itself, right? So this will make our traversal a lot easier. So first thing, merge child if number of children equal to 1. So just merge node 5 into 4. Okay, and then our tree will look something like this. And yeah, while doing this, we have to take care that the queries addressed to node 5 should get redirected to node 4. So this can be easily tweaked in the code, right? So let us proceed. So after having merged all the children that are single onto their parents, so now we can safely assume that each node has 0 or greater than equal to 2 children, right? So there is no single child. So either the node is a leaf node or it has 2 or more children. Cool. So now let us consider a node V, say node V. Now let us see all the nodes which are leaf nodes in the subtree of V. So which is the subtree of V? This is the subtree of V. So the leaf nodes are 9, 10 and 6. Now what we can see over here, that the product of the nodes, so how many nodes? So 1 2, so 2 into 2, that is we will do level wise product, right? Because that many parts uh, the product is going to get divided into. So the leaf nodes will get W upon the total product of the nodes till then, so upon 2 into 2. So this node will get W by 4 tasks if node 2 gets W tasks, right? So this is clear. So this can be represented something as, say, this is a node V and we are going down the tree. Say this has C1 children, this has C2 children, and so on up to the leaf. So what we can do is over here, that this level, it will have W upon C1 tasks to each node, right? If it is, and if it is leaf, it will end there. On this level, it will have W upon C1, C2 tasks for each leaf, right? And for the leaf nodes, again, it will say it is C3, so W upon C1, C2, C3, and so on. So let us assume that the subtree height is K. Now tell me what, suppose the product, that is C1, C2, C3 up to CK. So suppose this is equal to P. So what can be the minimum value of P? Now it is easy to guess. Now we know there are at least two children at each level, right? Because we have eliminated all the nodes that are single. So P will be greater than equal to 2k. So this brings us to the rough calculation that we have approximately log n nodes in one subtree, that we have to actually check to get a valid work distribution for the leaf. Now let us proceed with this idea.
So, moving with the next part of the solution. So, we start from the leaf and take product is equal to 1 over here, and then we start going upwards. So, over here, P will be equal to C1. Here, P will be equal to C1, C2, and so on. Now, why are we doing this? Now, we know that W mod P should be 0 for the leaf to actually have some work, right? So, P should be less than equal to 10 to the power 6 to actually have a chance of being a factor, where 10 to the power 6 is W max. So by doing this, we reach a arbitrary node after which P exceeds 10 to the power 6. It can happen. Then we can say that node is the highest node where there is actually a possibility of reaching the leaf if work is given to that node. So there is a possibility if P is less than equal to 10 to the power 6, then for a particular node, for node B, then work given to this node ends up at ends up at a particular leaf. Okay, so this can be easily calculated in n log n. Now let us move to seeing how we can actually calculate the work done. Moving forward, what we can see is that at every node, we can only look at those leaves for which P is a factor of V. P is a factor of W. And we saw what P was, that it was a product from the leaf up to uh, going upwards. And we break when the product is greater than W max, right? So now, what are the maximum of factors for W. So it is our first impression will be that the maximum number of factors are square root n, but this is not the answer. So the maximum number of factors for W max, they will be 240. Why? Because W is 10 to the power 6. Now this is a very good observation, and I will show you a series on OEIS which helps us do this. So this is the series on OEIS where we get maximal number of devices for any n digit number. And here for 10 to the power 6, the answer is 240. So there are 240 maximum divisors for numbers less than or equal to 10 to the power 6. So another important point to be remembered here is that queries should be stored. So this is very important because the method that we are implementing, we cannot answer queries online, right? So queries should be stored so that they can be answered offline. So how should they be stored? So we can maintain a vector of vector of say, I don't know, and then say mx, where mx is 10 to the power 5, and what we can do is for every query we can just push w. So we maintain the number of different w's for each query at the node v. Cool. Now let us proceed with this thought. Now, moving towards calculating the work done, what we can do is for every node v, we can store number of leaves I with factor I that we saw in the first part of our solution. That we go upwards from the product and we see what is the factor for each leaf, number of factors, right? Now here we have stored the queries for every leaf. So for query W in that node, for every factor of W. So here we will have to do prime factorization, and I will tell you how to do that efficiently. And it is a very well-known method, prime factorization of W. And then for every factor of W, what we do is that the total work done, work, we add in work leaves of I into W upon I. So what is W upon I? This term represents the number of leaves with this factor P, and leaves of I represents the number of such leaves, right? So I think over here we have calculated the total work done. Now the thing is that how to maintain the leaves array. So obviously we cannot maintain a separate leaves array for every node v, right? Otherwise the total complexity will go something like of n square, and this is not desirable. So let us see how we can maintain the leaves array efficiently. So what can be done is that we maintain a leaves array initially for the root. Okay, and as we go on to the adjacent node, we can fix the array. So now how this can be done? So for each node having p for every leaf, we update leaves of I plus equal to 1, right? And then we do the work on our node that we saw earlier, the total work done. Then we again iterate through leaves and leaves minus equal to 1. So what we see over here is we do the work on the leaf, and then we just replace the value of the leaf back to its original. So the value of leaves will be 0 before like before visiting that node, and also 0 after the work is completed. So the work is done, and then therefore we can maintain the leaves array in ON space with this pre-computation. Now let us check out what will be the time complexity of this solution. The time complexity for this solution, it will be O of n log n, which was the leaf factor operation that we did initially. that we went up from the leaf plus q into 240. So this is a very loose upper bound and it will not really be that high. And we are using at max, we are iterating over at max 240 factors to answer each query, right? Plus it will be w log w because we need to again find the prime factorization of w, like the factorization of w, and it will take w log w. So let us analyze this a bit. So n log n, it is very light because n is 10 to the power 5, and so it is okay. Q into 240, it is a loose upper bound. So again, this will be light. W log W, it is a bit heavy, but then again, it won't affect the time complexity much because the total operations are still well within 10 to the power 8. So the 1 second time limit is perfect. Now, having seen the time complexity analysis, now let's get to the implementation.
Now let us move on to the C++ implementation. So here initially I've taken input n, which is the number of nodes. Now here I've taken input the parent of I plus 1th node, and I have pushed it into a tree. So this is g of x is my tree. So sorry, g vector of vector is my tree. Now here I've taken input q, which is the number of queries, and for each query I am taking input two variables. V is the value of the node on which the query is, and w is the number of tasks to be executed by that node. Now I'm storing these queries in a vector of vector again. So for each query at the vth node, I'm storing in the vth vector, I'm storing the w, that is the number of tasks, and the query number, so that I can later pre-compute all the queries and then directly output it. Now I'm calling this dfs1 function. So dfs1 function, it is a simple dfs with albeit little changes. Now we go to this dfs function. So here I've taken in num, which is the g of v dot size. So it tells us basically how many children this v node has. So if the number is 0, then we simply put mp is equal to 1. That is no child. So that is the leaf node directly. So for leaf node, we have mp of 1 equal to 1. Now if the number of children is 1, then what I'm doing, we are merging the child with the parent node. So mp of 1, and I am doing a dfs on the first node itself. So I'm merging it. Else now we have more than one child, and then I'm calculating as I told you in the solution, that all these things, that a product should be less than w, and auto of u, so this is a normal auto of u, g of v, a normal dfs approach, and then in mp of 2 I'm iterating the dfs for each of the nodes uh, who are the children of the vth node. And here I'm calculating the product as we discussed, that we went up from the leaf to the top of the tree, right? So this is that approach, and here I am calculating the all the queries which are on the particular node v that is in consideration. So this is the C++ implementation, and now let us submit it and let us see if we get a correct answer.